But yeah, nothing to say about the exam. We're writing it. It's going to be great. It's going to be one for the ages. Let's see. So what we're going to do is keep talking about fluids. So we did most of it last week, really. We did the static parts and the buoyant forces and all that. But we got to get to this dynamic thing. Fluid dynamics. Already a question. Why are we doing a review session for an exam? Because I don't want to. So, let the fluid flow. Fluid flow. Hafner's going off the rails. He's not nice anymore. I don't want to do it in a review session, so we're not going to. So what we're going to do is dynamics. We're going to let the fluid flow. Who wants to win the Nobel Prize? I don't. That ship sailed a long time ago. My dreams are dead. But you might want to win the Nobel Prize, okay? And here is how you could win the Nobel Prize. If you see this candle. Oh, wait, we could do like a Schlierian projectomatic thing here. Whoa. Oh, my God. This is spontaneous demonstration. Okay. I was supposed to blow it out and look at the smoke. Now, if I'd shut up, it would do what... Okay. Oh, you see the laminar part? See how the flow is nice and smooth if I stop talking? You see how the flow is nice and smooth and then suddenly becomes all crazy pants there? You see that? If you can explain how it goes, what happens there, Nobel Prize, right? This is complete classical physics. Let's see if it works with the smoke. Oh, you can't see the smoke. Okay. Wait, that was keeping me warm. We're going to relight this bad boy because literally my fingers, I can't write on the chalkboard. But what we're talking about today isn't some quantum weird thing. It's just completely classical flow of completely classical material, but explaining things like how you go from the nice laminar smooth flow to the crazy turbulent flow. Can't do it, right? We can't do it theoretically. Yes, we can simulate it on a computer and blah, 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 blah. But in terms of the basic physics of it, can't explain it. There's no simple way to explain exactly when it's going to go all crazy like that, okay? So the point is, fluid flow, you would think, is just classical physics and easy. It's actually extremely complicated, extremely tricky. So what we're going to do is we're going to make 3 fundamental assumptions that will allow us, in our physics 125 mode, to understand fluid flow. One is we're going to make the Fuseli assumption and make it incompressible. Wait, no, that's pasta. What's the guy's name from Princess Bride? It's not Fuseli.
Fitzini.
What is it?
Fitzini.
Fitzini. That also sounds like pasta. I'm not sure. Okay. So it's going to be incompressible. So we talked about that before. Gases are compressible, but liquids are incompressible. So it's going to be a liquid is what we're trying to say. 2, we're going to make it non-viscous. Okay, so if we had, a month to spend on fluids, we would get into viscosity. And we'll mention it briefly today, but we're not going to do viscosity problems. It's not in the book. So what that means is that there's no resistance to flow. It's basically frictionless. It's the fluids we're going to consider are incompressible and they're viscous. And 3 is laminar. And basically that means it's steady and uniform. So that is this part of the little heat thing. The heat you saw in our shadogram there, or the smoke that you could see if we could see it better. Okay? Now, okay. So it's very hard to do anything in the real world if you make all these sort of things. So there's a very important video I want you to see that will inform the rest of your scientific career, no matter how short it may be. Let's see, here it is. This is like a great deal of my understanding of the world is based on this video. Okay, ready?
Does your dare do that? No. Yes, dig it. I thought you said your dad did not bat. That is not my dog.
Okay, thank you, yes. That is critical. Oh, there's that guy.
My pants have belt loops. I hold up my belt. I don't know what's really happening down there.
Okay, that's my other one, but okay. I think I showed you that before, I don't know, okay? So this is serious. I'm not screwing around here, okay? So the innkeeper has a dog. Clouseau asked him, does your dog bite? Assuming it was the dog right there. The dog bit him because that wasn't his dog. So that's all about assumptions, okay? I'm very serious. Read the scientific literature. And they'll be like, a long time ago, someone made a bunch of assumptions on a theory and derived a simple equation. There's never simple equations that describe the universe. They're always super complicated equations we can't solve, like fluid flow. Okay, but if you make a bunch of assumptions, you can get this nice simple equation that everybody likes. And this guy in 1600 applied approximations and assumptions to get that simple equation. And people used it responsibly. And then somebody needed to get tenure, right? And they write a paper and they're like, well, shit, okay, I'm going to use this equation. I'm not following the assumptions. And sometimes they'll do it knowingly and they'll say, you know, we're not under these assumptions, but let's just do it anyway, right? There's really, you know, what else can we do? Like, I'd actually prefer you do nothing, right? Then don't publish the paper. But sometimes people just break the assumptions on purpose. Sometimes people don't know they're breaking the assumptions, right? They don't even know that there's assumptions behind this approximation, okay? So if you're ever doing research and you see a simple equation that describes an effect, I guarantee you there's at least 10 assumptions behind it. The only simple equation in the world that kind of works is F equals ma. After that, everything is complicated, okay? So you're going to see in this lecture multiple times that there's like, we're breaking these assumptions over and over again, all right? It really happens. Okay, here we go. With that, I got to be really crazy today to stay warm, okay? It's going to be a lot of really fast movements. And apologies for the European stereotypes in that video there, okay? So, Clouseau somewhat inspires my occasional French accent that comes out. It's a little bit of a Clouseau thing, okay? Okay, so we need some new laws. Another thing I meant to write down is all this fluid stuff we're doing sounds very complicated. It is complicated, but the number of equations we're usually using is actually very small. The one you have so far is the pressure at some depth of a column, right, is the pressure at the top of the column plus rho GH, right? This is the static case. That's the one equation we pretty much did everything with last time. That and definitions of density and volume and, But the only physical law was pretty much that.